Okay, so they ask about, or they give you a situation where you have a couple of resistors, and they don't tell you which direction the current is going, but they ask, how would you determine the force on the proton in between these things? So they go off for a long distance, and I'll just assume that the currents are going to the right, okay, because they don't specify. So they do tell you that R1 is 10 ohms and that R2 is 100 ohms and that the voltage is 100 volts. So you know that the current through here is going to be 1 ampere. And I'm just going to draw the stuff on top. I'll just call this R2. And we'll say it has I2 equals 1 amp. And down here, it'll be green. So here we have R1 and I1 equals 10 amps. And we'll just have them going to the right. Now, it also says the proton, the distance in between these things is 3.33 centimeters. And the proton is 1/3 of the way up. So, call it about there. So this distance is going to be 1.11 centimeters, and that's going to be twice as much, 2.22 centimeters. And this is a proton, and it's going up at a velocity of 750 kilometers per second, which would be 7.5 times 10 to the 5th meters per second. Okay. Now we have to figure out the magnetic fields that are going to cause this thing to have a force on it. So we'll do one at a time. I chose to do the smaller one. Let's see, did I do the smaller one? Yeah, I did the smaller field first. So this is a lower current, and it's farther away, so it's going to have the smaller field. Why do I do this? Well, because then I can multiply by something to get the other field. We'll cover that. So anyway, what's the magnetic field from this? Well, B equals mu naught, permittivity of free space, I over 2 pi r. Okay. When you plug that in, you should end up with, let's see, we got 9.01 times 10 to the minus 6th. Okay. 9.01 times 10 to the minus 6th Teslas. Okay. And now the direction here, I chose the current going to the right. So by the right-hand rule, this is going to have the current going to the right and the magnetic field be going into the page. Okay. Now, for the current down here, well, this one is 10 times the current. Okay. So I goes up by a factor of 10 times. And also, so that's going to make the magnetic field go up times a factor of 10. And the distance, the radius, goes down because it's closer. So the radius goes down divided by 2. But because the radius is in the bottom of this formula here, that's going to cause the magnetic field to go up times 2. Okay. So when the magnetic field is directly proportional to the current, whatever happens to the current happens to the magnetic field. It's inversely proportional to the radius, so the radius goes down by a factor, the magnetic field goes up by the same factor. Anyway, so this ends up being 20 times the strength of that, which comes out to be 1.8 times 10 to the minus 4th Teslas. Now, this one, the current is going to the right, if you use your right-hand rule, then this is going to have the magnetic field coming up, and therefore these magnetic fields are going to be acting to cancel or fight each other. So you want to take the difference between these two. This is much larger, so if you take this and subtract that, you'll end up with a magnetic field, a net field of 1.71 times 10 to the minus fourth Teslas. Okay, and because the green one was stronger, okay, at least according to my diagram where it's going to the right, then it would be coming up out of the page. So up out of the page wins. I'll just put a dot here to remind myself that. Now, what does that do to the proton? Well, the force on the charge going through, F equals Q V cross B. And because these are at right angles to each other, the V cross B, or VB sine theta, just ends up being V times B. So when you multiply out for the force, you get the charge of a proton, 1.6 times 10 to the minus 19th coulombs. You get the velocity times 7.5 times 10 to the 5th meters per second. And you'll multiply times, I'm going to run out of paper here, but 1.71 times 10 to the minus 4th. Now, a Tesla is technically a Newton second per coulomb meter. And so the units actually, you end up with what you should end up with, which is always comforting. Coulombs up top, down bottom, meters up top, down bottom, seconds down bottom, up top, and you end up with newtons. And the final answer here would be 2.05 times 10 to the minus 17th newtons. Okay. Now, for the direction, we have the proton that's going in this direction. I always use my thumb like I'm hitchhiking. I'm going that way. I'm going to turn my hands so the my fingers are in the direction of the magnetic field, which is coming. Turn my fingers in the direction of the magnetic field, which is coming out, and therefore this is going to be pushing to the right. So it's hard to show, but I'll just say use the right hand rule. So the force on this is going to be going to the right, which is in the same direction as I have the currents. If the currents are going the other direction, it'd be pushed the other direction. So this would curve to the right. Now, this will not go in a circular path because it's not a constant magnetic field. As soon as you get closer to this wire, there'll be a stronger field from the top and a weaker field from the bottom, so it's not going to be a circular path. But that hopefully will help. All right.